Hi, in this video, we will talk about budget constraint and the consumer's problem. At the beginning of the section, we noted that we're interested in modeling a particular type of consumer's choice problem. In this type of problem, the consumer chooses the number of goods to purchase that best suits their preferences, while using limited amount of resources. However, a fact in life is that what we would like to have or accomplish is usually way more than what we can achieve with a given amount of resources. If you think about the typical consumption decisions, we're limited by one type of resource or another. In economics, we'll refer to these limits as resource constraints. It might be a fixed budget when you go on a trip. It might be a calorie budget when you go for some ice cream, or it might be a time limit that restricts the entertainment choices over the weekends. Naturally, a model for such a decision environment involves two major components: preferences and limited resources. Up until now, we spent a lot of time describing the utility function as a way to help us model the preferences. Now, we will turn to the second component of the model, the modeling of limited resources. To fix ideas, we will focus on the limited amount of expenses that the consumer can use on the goods. And we call this restriction the budget constraint. To introduce this idea, we will consider one of the simplest environments. A consumer is given a limited income or budget of Y dollars, let's say $10, to spend on two goods, labeled by 1 and 2. Let's say they're apples and bananas. It depends on a specific context where the word income may be more appropriate than budget, but the model stays the same, so we will use them interchangeably when we discuss models in this course. Given this limited budget, the consumer chooses the amount to consume, Q1 and Q2, when the prices of these goods are P1 and P2. Let's say $2 for each apple or banana. If I'm limited to a budget of $10 to spend on apples and bananas, what are the possible choices for the quantities? Well, it will have to depend on the prices of each good. Before I head to the checkout counter, I should not put too many fruits into my basket such that their total price goes above $10. If each unit of fruit has the same price of $2, apples or bananas, then I can buy up to 5 units of fruits in total. Any combination with more than 5 units of fruits would exceed my budget, so they are infeasible. And any combination with less than 5 units will leave some extra money in my wallet. And any combination with just 5 units would use up my budget. The whole point is that the money I spend on apples and bananas combined cannot be more than my budget. Our model of the budget constraint is exactly this idea. The limited resources require us to choose consumption bundles such that their costs do not exceed the budget. Our question at this stage is, what are the possible choices for the consumer under this constraint? Just like the idea in the example, the left-hand side of our budget constraint is the total amount of expenses spent on the two goods. With a $2 price on each fruit, I can buy 1 apple and 4 bananas, which will be $2 on apples and $8 on bananas, or 2 apples and 3 bananas, etc., etc. However we choose the combination of goods, the total expenditure cannot exceed the total budget or income. And that's our model of the budget constraint. You might have noticed that I wrote an equal sign here instead of a less than or equal to sign. In other words, this choice is further restricting us to use up all the budgets. This is a deliberate choice to make our constraint easier to work with, so we can keep the caveat in mind and proceed with our analysis for now. At this point, it is very useful to plot the budget constraint in the Q1, Q2 axis, just to see what kind of combinations of Q1 and Q2 are available to us under this particular budget of y, given these prices of P1 and P2. Let's say that we want to plot Q2 on the vertical axis and Q1 on the horizontal axis. Of course, this is just arbitrary choice, and you can certainly do it the other way around. But to fix ideas, let's put Q2 on the vertical axis for now. To make the algebra more apparent, let's use y as the placeholder for Q2 and x as a placeholder for Q1. In that case, the budget constraint can be rewritten as P1 times x plus P2 times little y is equal to big Y, which is the budget or income here. And now what we want to do is to isolate out little y and write it as an expression of x and all these other exogenous variables. So to do that, we subtract P1x on both sides of this equation, and that gives us y minus P1 times little x. And then we divide both sides by P2, and that gives us y over P2 minus P1 over P2 times little x. But remember, y is just a placeholder for Q2, whereas x is just a placeholder for Q1. So the equation is in fact Q2 is equal to y over P2 minus P1 over P2 times Q1. Now we can plot Q1 on the horizontal axis and Q2 on the vertical axis. Now on our slides, we plotted this function. This is exactly what we just rewrote on the boards. And to plot this graph, we realize that it has a Q2 intercept of y over P2 and a Q1 intercept of y over P1. The slope of this curve is minus P1 over P2. Now let's try to make sense of this graph with our previous fruit example. With $10 in my budget and $2 for each fruit, how many bananas can I buy at most? Well, to find this amount, I would think about spending all of my $10 on bananas. Let's say that is Q2. Now with $2 of fruit, I can buy at most 5 units. And that's exactly what the vertical intercept is telling us. The most amount of good 2 we can buy is the amount of good 2 we can purchase when we spend all the budget, y, on Q2. When we do that, the quantity will be y divided by P2. And that's exactly the vertical intercept on our graph. What about the most amount of Q1 we can buy with the same budget of y? Well, exactly. We're just going to spend the entire budget on good 1, and the amount we can get out of it is going to be y divided by P1. So these are the intercepts of our budget constraint. Now, notice that Q1 intercept does not depend on the price of good 2. Does that make sense? Absolutely. Because when we spend all the income on apples, the price of bananas is completely irrelevant. Regardless of whether it is 1 cent a unit or $10,000 a unit, the amount of apples we can buy is exactly the same, as long as the price of apples remain the same and our budget remains the same. Similarly, notice that the intercept with Q2, y over P2 here, does not depend on P1. Now, recall our earlier note about the restriction we imposed by the equal sign in the budget constraint here. The expression provides us with this downward sloping and straight budget constraint. But what we should keep in mind is that the constraint itself simply says that we cannot choose any combination beyond this line. Any combinations underneath this line would have been fine. For instance, I could have chosen 0 apples and 0 bananas, and then my total expenditure would just be $0. That's certainly less than the $10 I have, and it's totally feasible. Similarly, I can buy 1 apple and 1 banana, etc., etc. As long as the combination of goods I choose does not go beyond the straight budget constraint, it is feasible within our budget. This is why we call this entire region below the budget constraint the opportunity set. including the combinations along the straight budget constraint, but not beyond. In other words, a budget constraint expression with an equal sign plots the outmost possible boundary of the feasible set. An important insight from the budget constraint is that the prices of the goods and my budget will jointly determine the combination of fruits I can purchase. If the budget changes, or if the price changes, the set of feasible choices I can make will change. This is an important piece that drives the consumer's choice model, and it will come up repeatedly later on. You can also verify the slope of the budget constraint from the graph by dividing the vertical intercept of y over p2 by the horizontal intercept of y over p1. Then the slope is just rise over run, and then it gives you the expression of minus p1 over p2. Of course, the budget constraint is downward sloping, and therefore there must be a negative sign. It turns out the slope of the budget constraint is a very important element in determining the consumer's choices. Because we'll refer to it repeatedly later on, it is useful to put a name on this object. We will call it the marginal rate of transformation, or MRT for short. When Q1 is on the horizontal axis and Q2 is on the vertical axis, the slope of this budget constraint is exactly minus P1 over P2. This is the negative of the ratio between the price of the horizontal good over the price of the vertical good. The negative sign is very intuitive because as we consume more of good 1, then under the limited budget, the amount of good 2 we can consume certainly becomes less and less. Now let's look at a particular numerical example to see how budget constraint works. We will try to write down the budget constraint under a very particular budget and prices. Let's say that good 1 is pizza and good 2 is burritos, and their prices are $1 and $2 respectively. Now, let's say we have a budget of $50. What will be the budget constraint for the consumer? Please try to pause the video here. Do not flip back to see the previous expression we discussed, and just try to write down the budget constraint that is most intuitive for you. Even if you get it wrong, this practice is very helpful. So please take a minute to think about it and give it a try. This is a very important piece that we need to practice on. Do you have an expression? Now let's compare notes. The budget constraint I got is Q1 plus 2Q2, which is our expenditure, is equal to $50. Did you get the same expression? With a price of $1 a unit, every unit of good 1 will cost expenditure of 1 times Q1. With a price of $2 for every unit of burrito, for Q2 units of burrito, it's going to cost me 2 times Q2 amount of expenditure. So adding up the expenditure I spend on pizzas and burritos, they have to sum up to be my budget of $50 on the right-hand side. And there we go. That is the budget constraint. Just like we discussed previously, the vertical intercept is determined by the amount of good 2 I can purchase if I spend the entire budget on it. Now with $2 for each burrito, the total amount of burritos I can purchase is, when I spend $50 on good 2, and each one of them costs me $2, so the most amount of goods I can buy is 25 units. Instead, the horizontal intercept is going to be determined by spending the entire budget on pizzas, which has a price of $1 a unit. So the total amount of pizzas I can purchase is 50 units. And there we go. And the slope of the budget constraint is the negative ratio between P1 and P2, which is minus 1/2. You can get the same answer by dividing the vertical intercept by the horizontal intercept. Of course, we should bear in mind that any combination with expenditures below $50 are also feasible. So the consumer can choose any combination within the opportunity set, while all the combinations along the budget constraint are at the frontier of what is possible under the budget. We have interpreted the negative sign in the slope of the budget constraint, which we call MRT. Now let's use the pizza and burrito example to think about the intuition behind the price ratio. Let's say that we plan to spend the entire $50 of budget on burritos. And now let's say that from this point, we want to change our consumption plan. So instead of spending all of the money on burritos at this point of the budget constraint, I would like to purchase one slice of pizza. Because our previous plan already exhausted the entire $50 budget on burritos, now we have to back off on the number of burritos in order to free up some budget to purchase the slice of pizza we want. So how many units of burritos do we have to give up in order to buy the slice of pizza? Well, to free up $1, which is the price for pizza, we will have to give up exactly half a unit of burrito, because the price of burrito exactly doubles that for the pizza. And this is exactly what the measure MRT is telling us. In fact, this trade-off is true for any point along the budget constraint. Because we're already exhausting our budget, to purchase one extra unit of pizza, we will have to decrease the amount of burritos by 1/2 in order to satisfy the budget constraint. More generally, given the prices of two goods P1 and P2, whenever we want to purchase an extra unit of good 1, we have to decrease a certain amount of good 2 to free up some budget. And the amount of good 2 we need to free up is exactly the amount just enough to pay for 1 unit of good 1, which is P1. MRT tells us that the price ratio determines the trade-off between the two goods when we have to satisfy the budget constraint. And this is an essential piece underlying the consumer's choice problem. A very useful note at this point is that the budget constraint does not tell us which combination the consumers would choose. It simply tells us what choices are feasible. If I only like pizzas but not burritos, then I would spend all income on pizzas. But if I like variety, I might go with some combination of both. As long as the total expenditure does not exceed the budget, it is up to the preference of the consumer to determine which consumption bundle within the opportunity set best suits their preferences. Now, finally, with the preferences in place and the budget constraint ready, we are ready to move into the consumer's choice problem. In the consumer's choice problem, we're interested in finding the best choice that suits the consumer's preferences under limited resources. Now, with the help of the budget constraint to tell us what kind of choices are feasible under the limited resources, and in difference maps to tell us what combinations consumers would like to have given a particular preference, now we're ready to put the two pieces together to address this question. In previous lectures, we deliberately drew both the indifference maps and the budget constraint on the Q2, Q1 axis, because their coordinates are consistent with each other. This allows us to overlay the budget constraint graphically onto the indifference map. We have seen a two-dimensional budget constraint, and here on the right-hand side, we're illustrating a blue line as the budget constraint, overlaying on an indifference map. Now, in a 3D graph, what would a budget constraint look like? Well, it's going to look like a vertical screen that's inserted into the 3D box of a utility hill. And it would act as a screen that limits the consumer's choices on the lower side of this hill. So the consumer would like to climb up to the utility hill towards this corner, but the screen of the budget limits where the consumer could go in terms of the Q1, Q2 coordinates. Recall that in our model of preferences, the non-satiation assumption was in place to model the idea of unlimited wants. Without any constraint, the consumer would choose the farthest possible bundle towards the upper right corner of the Q1, Q2 dimension, or towards this corner of the 3D graph. where it points to the highest altitude we can reach on the utility hill. Such a point would provide the highest possible utility value. However, once the budget constraint is in place, the consumer can only choose within the opportunity set that is limited by the budget constraint. The question is therefore how to reconcile these two aspects by finding the most preferable consumption bundle that satisfies the budget constraint. So now let us focus on the 2D graph on the right-hand side and try to find the answer to our question. There are many possible choices in the feasible set under the budget constraint that we can choose from. But to find the best one, we'll have to break down the task into 2 steps. First, I would like to argue that the optimal bundle must be on the budget constraint itself rather than within the opportunity set. Why is that? Well, let me zoom in and focus on our 2-dimensional budget constraint and indifference curves. Let's pick an arbitrary consumption bundle within the opportunity set. Well, let's say this one. Can the consumer do better than this? Well, yes. Because we're still within our budget, the consumer can have more good 1 and more good 2 at the same time. So by moving this consumer's consumption bundle from our initial point to the second point, or the second bundle, we're still not going through our budget, and the consumer now enjoys good 1 and more good 2, so consumer's utility definitely has to be higher. But this process doesn't have to stop here. We can keep pushing up towards the upper right corner and improve the consumer's utility by moving up again and again and again until we hit the budget constraint, at which point we can no longer push up towards the upper right corner by increasing both good 1 and good 2. In fact, pick any consumption bundle inside the opportunity set. There must be some space between the budget constraint and this internal consumption bundle. So we can take advantage of this space by pushing up towards the budget constraint. And this is always more preferable to the consumer while remaining under the budget constraint. And this type of action only becomes impossible once we hit the budget constraint, where we can no longer freely increase both goods without breaking the budget. Now we have figured out that all the bundles under the budget constraint cannot be optimal for the consumer. We can turn to the second step, to focus on selecting the optimal bundle from all the points along the budget constraint. If we take a look at the graph, clearly not all points along the budget constraint provide exactly the same amount of utility. This point has very low utility levels because it's associated with a very light shade, whereas points toward the middle area tend to be more optimal because they are shown to have a heavier or darker shade to represent higher utility level or higher altitude on the utility hill. In fact, this point around here looks like it is pretty close to the optimal consumption bundle we can do within the budget constraint because it seems like it corresponds to a very warm color around this area. So how do we describe this optimal consumption bundle in a more formal and more general way? Well, in particular, if we can't visually see the shades that represent the altitude of the utility hill. Well, in fact, we will be able to describe the optimal consumption bundle by the shape of the indifference curves and the budget constraint. Now, I have just zoomed in again to our 2D graph on the right-hand side. Well, let's pick any point along the budget constraint. You will realize that if this point sits on the indifference curve that cuts through the budget constraint twice, once here and one more time here, then we can actually improve on this point and this point. Because any consumption bundle sitting between these cutting points will actually be sitting on an indifference curve that is higher than their indifference curve down below. And similarly, if you look at these 2 points again, we can keep improving them by moving towards all these points between these cutting points. And because there are many indifference curves very densely located between each one of these illustrated curves, we can always keep making these kinds of improvement by moving towards the consumption bundles lying between these 2 cutting points. And this kind of process only stops once we come down to indifference curve that only cuts the budget constraint on a singular point. And in our graph here, when the indifference curves are smooth, the highest indifference curve we can reach within the budget constraint will be the one that only just touches the budget constraint. In other words, it is just tangent to the budget constraint. We would like to reach higher indifference curves above, but our budget constraint would not allow that. So it is no coincidence that the optimal bundle that we spotted by looking at the shades of the graph just happens to be the tangent point between the indifference curve and our blue budget constraint. If you look at this graph closely and try to draw more indifference curves, you will realize that there is only one point where any indifference curve is tangent to the budget constraint. And this unique tangent point is the optimal consumption bundle for the consumer. At this point, I would like to remind you of 2 facts we have established so far that are driving our search towards a tangent point as our optimal solution. The first is that our indifference curves are convex. What that means is that if we connect any 2 arbitrary points along any indifference curve, all the points sitting along the connected proportion will always sit above the curve itself. The second fact is that the bundles that sit on higher indifference curves are more preferable to the consumer according to our preference relationship. It is these 2 facts together that tell us to focus the search along the budget constraint that sits within the connected segment of the indifference curve between any 2 cutting points. Because the indifference curve is convex, the segment of the budget constraint connected by these 2 cutting points along the same indifference curve must sit above the indifference curve itself, and therefore are more preferable. Understanding the insight would help us to locate optimal choices in the consumer's problem even when the indifference curves are shaped in a way that is not tangent to the budget constraint anywhere. We will see such examples later in this course. Most of the time, the budget constraint cuts the highest indifference curve by being tangent to it. This is the case we discussed so far, which would produce an interior solution. That means the optimal consumption bundle involves consuming both goods. But in some special cases, we may have what we call a corner solution. This is when the optimal choice is at the Q1 or Q2 intercept. In other words, the optimal choice involving consumer positive amount of one good but 0 amount of the other good. What determines whether we have interior solution or corner solution is the shape of the indifference curve. We will focus on the interior solution case for now, and we will return to discuss the case that involves corner solutions in later part of this section. Now we have solved the optimal consumption bundle graphically. This approach is very intuitive, but does not allow us to precisely pin down the exact quantities of good 1 and good 2 that is optimal for the consumer. So in order to get a more precise answer in terms of quantities of consumption, we will transition towards the algebraic approach to find the optimal bundle. But before we dive into the full algebraic way to tackle this problem, we will first try to summarize the key insights of our tangent point solution. To understand its economic intuitions, I extracted out the most essential pieces of our budget constraint and indifference curve graph and put it here. So we can focus on the indifference curve that ended up being tangent to the budget constraint. Now, let's think about the basic geometry. If two curves are tangent to each other, then at the tangent point, it must be the case that the slope of one curve is equal to the slope of the other at this particular point. In fact, we have been preparing for exactly this moment. The slope of the budget constraint is the negative of the price ratios of the horizontal good and the vertical good. We call this object the MRT. And the slope of the indifference curve is the negative of the ratio between marginal utilities of the horizontal good and the vertical good. We call this object the MRS. So when we have a tangent point as our optimal consumption bundle, then this optimal bundle must satisfy the condition such that the slope of the budget constraint, which is MRT, is equal to the slope of the indifference curve at this point, which is MRS. This is an essential piece of insight coming out of our graphical analysis, and it will play an essential role in our full algebraic solution in the consumer's problem. There is no need to memorize this expression as a formula. The advantage of our algebraic solution later on is that all these expressions fall out of that approach very naturally. So you will see that in the next video, but for now, it is very useful to think about this underlying intuition hidden in this particular expression. To think about the expression more intuitively, I find it very useful to rewrite the expression slightly. With our tangent condition, we have MRT, which is minus P1 over P2, is equal to MRS, which is minus U1 over U2. Now, with the negative signs cancelled out on each side of this equality, we would have P1 over P2 is equal to U1 over U2. Now we're going to rewrite it by dividing P1 on both sides of this equation and multiplying U2 on both sides of this equation at the same time. What we're going to end up with is the following. By dividing P1, we have 1 over P2 is equal to U1 over P1 times 1 over U2. And then by multiplying U2, what I get is U2 over P2 is equal to U1 over P1. And that is this condition we listed on the right-hand side. Now let's think about this expression a little bit more. U1 over P1 or U2 over P2 have a very intuitive interpretation. U1 is the marginal utility. It tells us the utility I would receive from one additional unit of the good. Let's say 10 extra utilities from one extra apple. But if each apple costs me $2, then how much extra utility can I get if I spend an extra $1 on apples? Well, it is exactly the marginal utility, which is 10 units, divided by the price, which is $2, or U1 over P1. So every extra $1 spent on apples would increase my utility by 5 units, which is 10 divided by 2. In other words, U1 over P1 or U2 over P2 are telling us how much extra utility the consumer will gain if they spend an extra $1 on each one of these goods. Now let's try to consider a thought experiment where the consumer chooses between apples and bananas. Now let's imagine that the consumer holds a handful of dollar bills and stands in front of two different jars, an apple jar and a banana jar. Now, if I tell you that the next $1 the consumer puts into the apple jar is going to give the consumer 5 extra units of utilities, whereas the extra $1 into the banana jar is going to improve their utility by 4 units, where should they put the next $1? Well, of course, the apple jar. The $1 will get 5 units of extra utility instead of 4 by putting into the banana jar. In other words, the consumer would always spend the next $1 on the good that provides a better bang for the buck. Now, as you put more and more money into the apple jar, perhaps the marginal utility from Apple decreases because now the consumer have a lot of apples. Now when the marginal utility per dollar spent on apples drops below 4, in this case it becomes 3, do you still put money into the apple jar? Well, no. Now the banana jar will give you a better bang for the buck. So you should put money into the banana jar now. If you keep going like this, at the end, the marginal utility per dollar will end up being very similar in both jars. And that's exactly what the tangent condition is stating. Now let's consider a variation of the previous thought experiment. Instead of having dollar bills in the hands of the consumer, let's suppose that someone had already arbitrarily put all the money into the apple jar. But what you can do is you will be able to move all those dollar bills between the two jars to improve the utility of the consumer. Let's also suppose that when all the money is in the apple jar, each dollar into the banana jar will bring the consumer extra utility of 20 units. And each dollar taken away from the apple jar will reduce the utility of about 2 units. Would you be able to improve the consumer utility by moving money around? Well, yes. By moving a dollar from the apple jar into the banana jar, you will increase the consumer's utility by 20 units coming from the banana jar, but you will only lose the consumer 2 units of utility from the apple jar. So on the net, you're increasing the consumer's utility by 18 units. Now, what if the marginal utility per dollar for apples are higher than that for bananas? Well, then you would do exactly the same thing by shifting money into the apple jar from the banana jar to improve utility without using extra budget. That's exactly the same idea. Let's look at our graph again. And let's pick a point on the budget constraint. Let's say here. At this point, we have a lot of Q1 and very few units of Q2. In other words, we already have a lot of expenses in good 1, but very little in good 2. In addition, at this point, the indifference curve is flatter than the budget constraint. If we write down the tangent condition, this means that the absolute value of the indifference curve, which is MRS, is less than the absolute value of the budget constraint, which is MRT. Or we can rewrite it as U1 over U2 is less than absolute value of P1 over P2. Of course, with the negative signs. Now, we take away the absolute value and negative signs together, we're going to have positive values of U1 over U2 is less than P1 over P2. And we can rewrite this again into the form of per dollar marginal utility. And when we do that, we're going to end up with U1 over P1 is smaller than U2 over P2. What does that mean? It means that now good 2 is offering us a better bang for the buck comparing to good 1. So now what do? Well, we should shift our expenditures from good 1, which is here, towards good 2 by traveling up the budget constraint. On the contrary, if we're at a point that's around here on the budget constraint, we have a lot of expenditure on good 2 and very little expenditure on good 1. And over here, at this particular point, the consumption bundle is sitting on the indifference curve that is steeper than the budget constraint. And then all these inequalities will have the opposite sign. What that means is that at this particular consumption bundle, the per dollar marginal utility for good 2 is lower than the per dollar marginal utility on good 1. So what do? Well, we should rearrange our expenditure such that we spend more money on good 1 and take out that money from good 2 to improve our utility while staying on the budget constraint. Through these exercises, we're trying to establish the intuition that if a consumer's optimal consumption bundle involves consuming both goods, then it must satisfy two different conditions. One, the consumption bundle would exhaust all the budget we have by sitting on the budget constraint itself. And number two, at this particular bundle, the marginal utility per dollar will be balanced between the two goods. These two conditions are the keys to solve the consumption's choice problem. Please hold on to them and we'll revisit them very soon.